Hi everyone. This is a demo video for EE533 Lab6 of Team4. And part one is to build a 64-bit synchronous ALU. And we build this ALU all in Verilog. And now let's see how we build it. So first, we build a 4-bit carry lookup adder instead of carry ripple adder because it would be more efficient. And then we instantiate the 4-bit adder to a 64-bit adder. And now let's look at the 64-bit ALU. And as you can see, we have 4-bit control bits since we have 10 functions. And they are add, subtract, and, or, XNOR, compare, logical left shift, logical right shift, substring comparison, and left shift, then compare, and right shift, then compare. And since it is a synchronous adder, a synchronous ALU, so we need to put we need to have always sequential logic to get our final result and overflow. And this is a combinational logic to select each function. Okay, so now let's see the simulation. Okay, so this is the simulation waveform for our ALU. And okay, so I want to change this to decimal so that you can see the add and sub better. And oh, I think it's dark. Okay, okay, now it's okay. Okay, so you can see. Okay, I think I need to show the table first. And you can see this is our um result result table. So you can see 0 means add, and you can see 20, 30, 50, and 1 means substrate, and you can see 50 substrate, 20, 30. And then let's back to hexadecimal, hexadecimal, hexadecimal. Okay, so then let's look at the compare and the logical shift as example. Okay. So you can see uh, when ALU control is 5, it means that we are compare this A and B, and if they are equal, the result is 1, and if they're not equal, the result is 0. And then let's see. Then let's see the shift, and this is a logical shift, and because in our code we shift we we shift A left by the value of B bits. So you can see here is 3, which means that 1 times 1 multiply 2 power of 3, which is A, and right shift is dividing, and I think A is substring compare, and 9 is shift then compare. I think is left shift then compare. Uh, left shift then compare means that we need to shift this A first, and then we compare with this compare value. And as you can see, um, 3 times 2 power of 2 is 12 and equals to C here. So it is 1. Okay, so after that is the part 2. Part 2, we first build the register file in Verilog. And as you can see, this is we have 32 registers, each with 64 bits, and we have 2 reports, which uses um, the value of RS and RT as index, and they are 3 bits and 1 write ports. And and then we use ipcorn to build our instruction memory and data memory. And so this is our instruction memory. So so it has 512 entries that um, that is 32 bits, and this is a dual port um, memory or block RAM. So we can read the instruction from it, and we can also write or loading instruction into it. And we can see our data memory is 200 is 8 bits, and which means 256 entries, and each one is 64 bits. Okay, so now let's look at the part 3. So in part 3, we building our pipeline data paths, and so basically we design each stage separately first, and then we instantiate each stage in the top module. And as you can see, this is the top module, and we have and we leave input and output ports for the preload and for the verification. And we have a start input port to start a pipeline, and we have the and then the clock port and the reset port. So first, let's see one by one. First is the PC. It's a PC stage. So it's basically PC plus 1, and then is the IF stage, and in this stage we will fetch the instruction, and ID stage we will decode the instruction, and EX stage. Since there's nothing for now, so the EX stage is just a pass through, and then memory, the memory stage. Then as you can see, we instantiate we instantiate all the stage in the top module to build our pipeline. Okay. So before before we see the simulation waveform of the pipeline, we need to preload the instruction into the pipeline first. So um, next, I will show you how we build our preload module. So the preload module is basically a finance state machine. So it's also a software hardware interface um, because we will load our input address and our input data to the output port, and 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 this output port will then connect to the pipeline input port that we leave for the preload of the instruction memory. And we use state machine to control the instruction load process. And as you can see here, we have seven states. And so let's look at the write memory stage directly. And as you can see in the write memory stage, we the the output um, the output memory address and the output memory data will get the input, and then we instantiate the preload module and the pipeline module in the top module, and you can see here the output of the preload module is the same with the input of the pipeline instruction address, instruction Y, and instruction Y in enable port, so that we can use this preload interface to to preload the instruction before we start the pipeline. And, and then let's see. Okay, so then next part will be the simulation of the pipeline. We'll turn off this first. Okay. Um, so let me first explain how we verify our pipeline. Okay, so before we see the simulation waveform, I want to explain our test bench logic. So what we did is basically load the value of data memory address real to the register file 2, and also load the same value to the register file 3. And because um, there's no storing and forwarding in this Lab6, so we need to insert um, 3 knob, and then we will store the value in register 2 to to the to the address 1 in data memory. And so in test bench, we first initialize the instruction memory and the data memory, and then we first load the instruction memory and the data memory. And remember, because we have already left the preload port for the instruction memory and the data memory, so we will first preload the instruction memory and data memory, and then after this we start a pipeline by give 1 to the start signal, and we will run for 6 clock cycles, and then we will we need to wait for the data write the data write back, and we will stop the pipeline, and then we give. And remember here, we have leave the port for the for verification of the result. So so basically we give the address and see what it will give to us in the output port, in the result port. So now let's see the waveform. Okay, so as you can see, this is the simulation waveform. And you can see first, we load the data memory and the instruction memory, and then we start a pipeline. We start a pipeline and we wait for all the instruction completed. And then we stop the pipeline here, and sorry, okay, I think it start. Okay, so you can see here, we give the value of the address, and we will see the corresponding value in that address. And for example, address real in data memory, the value is 4, because you can see here the value is 4. And address 1 in data memory, you can see here is 2, is and you can see the value in the register file. The value in register file 2 and register file 3 is all 4, which is the value in address real in data memory, because we load this value to the register 2 and the register 3. And let's see the value in address 4 in the data memory, and you can see the value in address 4 in the data memory is 4 because we store the value in because we store the value in register file 2 to address 4 in the data memory. And you can see here the value in address 4 in the data memory was 64 before, and now it is 4. Okay, so uh, so we end up our simulation, and it proves that our pipeline um, works well. Okay, that's it. Thank you.